all, welcome to part 5 module 6 computer networks. So we were discussing the TCP protocol, the core transport layer protocol TCP in detail, and in the last video, so it's again a continuation of what we seen in part 4. So watch it and come to this. So some more details on TCP we will see here, the TCP facilities. So you could see that TCP is providing a stream data transfer, particularly some byte stream transfer. From the application's point of view, the TCP features is transfers a continuous stream of bytes. So application will be viewing like the application is giving some stream of byte to the sender process, and at the receiver side from the process the application is receiving a stream of bytes, but on the background the streams will be collected and it's given as segment, and at the receiver side the segment is again converted back to stream of bytes, and those things will be done by the transport layer TCP entity, right? So the TCP does this by grouping the bytes in TCP segments which are passed to the network layer, and TCP itself decides how to segment the data, and it may forward the data as its own convenience. So, and that grouping everything will be done. So we have that connection establishment, connection parameter, socket, all those things will be involved in this. And regarding the reliability aspects of TCP, the TCP assigns a sequence number to byte transmitted and expects a positive acknowledgement from the receiving TCP. So positive acknowledgement those things actually extended with selective acknowledgement and all. So minimum it will expect something called a positive acknowledgement. So as soon as the TCP entity is getting a positive acknowledgement, it will assume that the data successfully reached the receiver. And if it is not getting it, what it will do, it will try retransmission, and that is how it is providing reliability. It will always ensure that the data correctly reaches the receiver side, of course by the error detection scheme and retransmission, and also with the help of the sequence number, acknowledgement number and timeout. So everything will be there, so you have that idea in your brain, and all those things that we already seen, all of them will be executed in a typical TCP. So ultimately this use sequence number is helping you to do all this. So if the acknowledgement is not received within the timeout interval, the data is retransmitted. That is one situation, and also the data is received at the receiver side but it is erroneous, and that time also a retransmission will be done. So the receiving TCP uses the sequence number to rearrange the segments when they arrive out of order. So that is another attraction we have, and to eliminate duplicate segments. So two cases where there sometimes the same TCP means that fragment may be coming multiple times, and so duplicates can be filtered with the help of the sequence number. If the duplicates were coming, their sequence number will be same, so that will be discarded in that way. And also out of order frames also you can expect the frames may come in any order, and that time by looking at the sequence number is typically given for bytes, right? So for the first segment, sequence number is actually the very first byte of it. What is the sequence number? The bytes will be numbered, right? And maybe so we have the byte stream coming like byte 0, byte 1, byte 2, etc., right, up to some byte 100, then followed by what is the next byte, say byte 101, 102, etc., some 200, something like this. If that is the case, I am dividing it into say 100 bytes in one segment, and this first segment will be given a sequence number of 0, means the sequence number of the very first byte. Now if we look at the second segment, its sequence number will be, right, its sequence number will be 101. That is nothing but the the second segment's first byte sequence number. So in that way it will give. So by looking at the sequence number, S0 one will be taken first, then 101 will be taken. By looking at its length and all, so it will do that reordering, and of course if, duplicate filtering. So altogether it provides a reliability in a typical TCP. And what about flow control? The receiving TCP, when sending an acknowledgement back to the sender, also indicates to the sender the number of bytes it can arrive. So something like we have a concept called window size. So the problem is actually because the sender is sending too fast than the receiver can handle, right? Now what we will do is at the receiver side we will maintain some kind of a buffer, and what is sender is fast and receiver is slower, then all this information will be buffered, and from this buffer the receiver will be taking the data. Now at any time maybe what is the buffer size left, right? So that the receiver will be communicating back with the sender. For example, initially the buffer is of some 1000 byte. I'm just taking an example. And after a single communication, out of the 1000 byte, some 100 bytes are filled, right? 100 byte. So in the next subsequent communication from receiver back to the sender, maybe a reply or something, this remaining capacity, so 1000 out of 1000, 100 byte is filled, right? So what remains? 900 byte. So that the receiver will be communicating back to the sender. So by looking at it, sender will understand what is the remaining buffer capacity at the receiver side, and accordingly the sender will slow down the data which is to be given to the receiver. So that is what it's trying to say. It indicates the sender's the receiver will be indicating the sender the number of bytes it can receive further beyond the last received segment, so without causing overflow in its internal buffer. So the buffer overflow should not be there. So like that, at every step the receiver will be communicating back to the sender. So accordingly, by looking at the sender's situation, the sender will correctly send the data. So this is how it is achieving flow control. And this is sent in the acknowledgement message, maybe for communication from the sender to receiver. And when receiver is sending the acknowledgement back, that time it will mention the maximum capacity of its buffer by telling the highest sequence number it can receive without problem. So right now I received from 0 to 499. Now I can receive some 500 more. So the highest sequence number it can receive without any problem is 999, something like that. So in any ways it should be communicated back. So this is one typical procedure being used in a TCP. So multiplexing along with the flow control, we have congestion control also, that is not highlighted there, but together we have that smart algorithms that will taken care. The flow control concept we discussed, and it will look into the network as layer aspect, and will be doing it. So multiplexing, so the same concept, the at the sender side, a number of process will be executed, and all of them want to have a different TCP connection at different receivers. But from this machine outgoing, we have a single connectivity, and that will be going here. Now as soon as the information is coming here, one path will be taking the communication between with this one and this one, and another path may be taking it to another device where this process, this one may be trying to communicate with this one, whatever it is. So this what is shown here is the logical connection, maybe this dotted portion, but ultimately physically all of them should be multiplexed like this, right? So many to one. So this is again taken care by the TCP ended, and also at the receiver side, when the thing is coming, it has to be demultiplexed to the correct process by looking at its socket identifier, right? So with the help of the port number and IP address together, that multiplexing and demultiplexing will be done, and it is correctly delivered to the receiving process, right? Yeah. So hope you have that idea. And the logical connection, the reliability and flow control mechanism described above require that TCP initializes and maintains certain status information for each data stream. So a connection will be identified by a set of status information. So it includes the socket details, something we already seen. In addition to that, the sequence number, the window size, the remaining window size of the receiver, and together it defines a logical connection, right? So because when we have this communication, we have to keep all those things. The communication endpoints will be identified by the socket details, socket identifier, and sequence number is needed for the reordering purpose. Window size is needed for the flow control. So together it defines the logical connection. So each connection is uniquely identified by the pair of sockets used by sending and receiving process, something we already seen previously. And full duplex TCP of course provides a concurrent data stream in both direction, right? Now let's see a typical structure of a TCP header. I just explain briefly here, and more details of each and every fields we will see in the subsequent video. So it starts with a sequence, the source port number and a destination port number. So the source at the center side, we have a source process, right, which is trying to connect with the receiving process, the destination process. So both are will be uniquely identified by the 16-bit port number, and using 16-bit we could have a 2 power 16 different ports numbers possible, say 0 to 2 power 16 minus 1. Out of them, the first 1024 are given to well-known applications, known to be well-known ports, and the remaining some are used in temporary basis, and some are reserved for the well-known applications. So like that we have the classification, we will see this. So that will be mentioned clearly here. Now the next 32 bit is exclusively given for the sequence number, and we already seen what is role of sequence number, mainly for reordering and ensuring reliability and all. And similarly we have the concept of acknowledgement number, and maybe in the data link layer, when we discussed, I explained you clearly why the sequence number is needed. In addition to that, why acknowledgement number is also needed. That situations I explained already, and for the same purpose here also we have the acknowledgement number. And typically what is the acknowledgement number? The last received sequence number plus 1, because what the receiver is expecting next, that will be the acknowledgement number. Okay. And then we have a 4-bit header length. Why header length? You could see it's like the first row is something like 4 byte, right? 31 bits or 4 byte, and the second row is again another 32 bits or 4 byte, and third row is another 4 byte. Fourth row is again 4 byte, and fifth row is also 4 byte. So like that we have a 5 fixed 4 byte fields. So together it makes it as a 20 byte fixed part of the header. But if you look at the option, just like a IP protocol, the size is something same for both. It is varying from 0 to 40 byte. So together sometimes we have a TCP segment without any header, that option, so that the minimum size will be 20 byte. But in worst case, if you have the complete option, the size will go up to 60 bytes. So the actual TCP header size will vary from 20 byte to 60 byte, and which is a variable number. So specifically sometimes it may be 28, sometimes it may be 32. So that number you have to mention here, the 4-bit header line. The same field like our when we discuss the same thing in IP, and as it is a 4-bit number, to represent any number, say 60, you need 6 bits, right? So here it is only 4 bits. So what we are we are scaling down. So the 32 bit like that we will group, right? Every 4 byte will be treated as 1, something like this, or we will this 2 power 6 by 2 power 4, like that we will group. Okay, so the actual header size, whatever it is, we will divide it by 4, and that divided value will be stored here. So when you divide this 60 by 4, it will be 15. So 15 you can easily represent it with the 4 bits, say for all 4 ones, if that is the case. If it is 20 byte, that will be divided by 4. So that is a common procedure. What will be the actual header size? Same thing we discussed in detail in when we discussed IP, same procedure. Whatever the actual IP header or TCP header, that will be divided by 4, and that divided value, scale down value will be stored here. And at the receiver side, that 15 again it will be multiplied by 4 to get the original header length. So accordingly it will take here 20, it will be 5. So 5 to 15 is a valid value here. If any value other than 5 to 15 is stored here, maybe say 3 or 2, that is error case. Everything will be reported accordingly. Now there are some 6 bits were reserved because it couldn't find a proper meaning. Maybe they thought of adding more flags here, but anyways when they have that protocol, initially there were 6 flags, and they were urgent urgent flag, acknowledgement ACK flag, push flag PSH, restart flag, synchronize, that is SYN, and finalize connection FIN. So like that 6 flags were there. We will see them in detail where it is needed and all. Okay, so with different scenario, mainly with the connection establishment we are using SYN, and restart is again connection restart, of course, and finishing the connection. Push acknowledgement, of course, if it is containing some acknowledgement information, this flag will be one. Urgent and push we will see. Okay. And another field is 16-bit window size, something I already told you. This is how it is achieving the flow control, the receiver window. What is the remaining capacity I have? What is the remaining window size I have? Something like I already taken in the previous slide. So that is the total buffer size, say it is 1000 byte, and with the current communication some 100 byte is filled. So what remains? Some 900 more byte I can receive. So in the reply communication or in the acknowledgement communication, that 900 will be stored here, so that by reading it the sender can understand 900 byte can be more sent to the receiver, not more than 900 bytes. So like that the window size will be mentioned in using a 16-bit field. So using 16-bit, what is the maximum window size you can mention? So that is so 2 power 16. 2 power 16 is 2 power 6 into 2 power 10, that is some 64 kilobyte. And it is a very small value. just 64 kilobyte, but normally we have a buffers of size some 1 MB and all, at least, right? So that time we typically have a scaling where this will be multiplied with some 2 power 14, but this 14 extra bits, so to 2 power 16, 2 power 14, it will be giving you some 1 gigabyte range, right? So that is a typically pretty good size for the header. So this will give you some 2 power 30s, but this extra 14 bits will be storing in the option field. So like that, there are many different cases for the option. Anyways, we will see them in detail. And in the next row again, that 16-bit TCP checksum, UDP checksum we saw in detail, and IP checksum also we saw. IP checksum is particularly for the IP header only, but if you look at the UDP checksum or TCP checksum, that is together for the header, TCP payload, and also for a pseudo IP header. In case of UDP header, UDP payload, and also for a pseudo IP header. Right, all the three things were taken and the checksum is calculated in details. This was that part 4 video lecture UDP, and that time I discussed in detail how that checksum calculation is done. The same procedure is being used here also for the error detection purpose. But in UDP, that checksum field is provided as an optional field, but here it is a mandatory field because we need that reliability. Of course, we are not ready to compromise it at all. Option is 0 to 40 byte, and one thing that we can store in the option field is that window scale factor, like that 14 bits I explained. And there are other cases also. We will see what are all different options, and followed by that we have the data. So hope you get an overview of this header, but of course I will dedicate the next video for more details of each and every field, right? So that time it will be very clear for you. So with this, let's wind up this part. Yes, thanks for watching.